So, this is Windows overflows, and we're going to talk about these strange things, the thread environment block and the process environment block, and compare stack-based buffer overflows with structured exception handler exploits. So these are the two things. Like I say, the first paragraph in the book tells you better know these things. You have to go off and look them up on Wikipedia. These things are actually quite disturbing because you are not supposed to use them and everybody uses them anyway. So this means they're writing code that I guess is not guaranteed to be sustained by Windows. Here's the point. You remember how you run a program, it's a process, but the process is just a container for threads, and the threads are what actually gets CPU time because they each move forward. So it might just have one thread, but most processes have many threads. So the thread environment block, also called the thread information block, has a bunch of information about the currently running thread. It is officially undocumented for Windows 9X. Windows NT, they document only a small portion of it at Microsoft, but apparently a lot of Windows 32 programs use the undocumented portions of the thread environment block. So somebody figured it out, and this knowledge became common, and people started using it. You can get a lot of information about a process without calling the API. And I don't really know why they don't just use the API, but perhaps the API functions are inconvenient or incomplete. So you can get the last error from the thread, you can get the import table for the thread, the startup arguments, and more. And the most important thing to us is the structured exception handler, which is right at the start of the thread information block at location 0. The FS is a segment register. The segment registers themselves are pretty bizarre and insane. There was a long dead early processor that broke memory up into segments and had pointers to the different segments, and nobody uses it anymore exactly, but it's still hanging around in the processor, these registers. And anyway, the FS points to the thread information block. And so you've got the bottom and top of the stack here, and you've got the SEH, which is the thing we're really interested in today. So FS and GS are segment registers. On Windows 32-bit, FS points to the thread environment block. On Windows 64-bit, it is somehow more complicated, and there's links here to articles that go into it. Anyway, the process environment block is a term I didn't know until today. This is an opaque data structure, which means it is something you are supposed to use with functions they provide you, but you're not even supposed to know what's inside it. This is apparently a real computer science thing. You can define a data structure and limit what you're allowed to use it. So the values are only supposed to be manipulated by the routines they tell you to use, and Windows NT uses it internally, but it's only supposed to be used by internal operating system functions. But even though Microsoft only documented a part of it, a lot of other people figured out a lot more and use it. So this makes the world of Windows programming even more insane than I thought it was, that normal legitimate programs are using these hacky workarounds by using things that are not approved by Microsoft. I would think that would be terrible, because Microsoft even warns you they might change this in a later release, and they're not going to care or tell you because you're not supposed to be using it. But anyway, so here's what's in the process environment block, a link to tell you whether it's being debugged, some parameters, some routines, the session ID for it, and there's a whole lot more added in. So, in the simple case, this is the classic technique that we've used in Linux quite a bit. You have a buffer overflow in a variable, and you overwrite the saved return address so that when the program tries to return from a function call, it loads that number into the number you have under your control into the instruction pointer. Then you have an exploit on the stack, and you put in the instruction pointer something that goes to an op sled, which slides down the sled and executes your egg. And that is the classic buffer overflow that we've been doing. So this name has an overflow. You put in a name, you run in all an op sled and an egg. Then down here you have padding to get to the EIP, and the value you put in the EIP will jump back to an op sled and execute the egg. That's how you take over a machine with a classic Aleph-null type buffer overflow. Now, in Windows, it turns out to be quite handy to use the structured exception handler instead. And we've already done something similar in Linux quite a bit when we targeted the global offset table, where you don't write directly into something that goes into the EIP, you write a pointer that we loaded in later into the EIP. It amounts to about the same thing, but the exception handler is what handles program errors. So you overwrite the SEH and then you trigger an exception by doing something illegal, it calls the exception handler, and the exception handler now points to your NOP sled and the injected code. So this is how this one looks. You overflow the name, you put in the NOP, you put in the egg, you put in the padding, and down here, you don't target the stored EIP, you find the SEH record, which is also available, and change that. Then you trigger an exception somehow. So this turns out to be quite handy to defeat ASLR. Remember, ASLR means that all the processes are in random memory locations, at least all the ones for which ASLR is turned on. And as we'll see, it's not really turned on for all the processes. So that's one easy way to defeat it, is to just attack the process that does not use it. But you can also do more. What you do is, and you'll do it in project 15, is you do not refer to any absolute addresses. What you do is you find a jump ESP or something else like that, and you put your thing so it starts at the stack of the start of the stack. So the address you put in there is the address of a jump instruction that will jump to a register, and now you don't need to know where your code is. You just jump onto the stack wherever the stack is, and you put your exploit on the stack. So we'll play with this. This is the simplest case of return-oriented programming, where you do not refer directly to an address. You said you call an instruction that's already in the operating system. You find a jump ESP somewhere and go there. That means that you do have to have some code with a fixed location, but that's always the case in Windows. There's always some parts of Windows that is not randomized, and you can hunt through that to find the instructions you need. All right, now in the old version of the structured exception handler, they left the structured exception handler in EBX. So you would register just right there telling you where it was. So that kind of undoes all randomization. In order to prevent this, the newer versions clear all the registers. So the structured exception handler is not just in a register, but it's still on the stack. And we're going to be using that in project 15. So the way you do that is, since it's on the stack at extended stack pointer plus 8, all you have to do is pop and pop, which will remove the top 8 bytes from the stack, and then return will now return, thinking it's coming back from a subroutine, and it'll assume the next value on the stack is the extended instruction pointer to put back in. So it doesn't matter if it pops into EAX or pops into EBX, just find any place in code where it does pop, pop, return, and jump there. And it will automatically run to the structured exception handler. So that's pretty cute. Anyway, so there are frame-based exception handlers. And what this is, what's going on here is, when you are running a program and it has an error, it could go, the first thing it does is tell the program, I have an exception. And the program now has an opportunity to run exception handlers that the developer put in there to handle errors. And if the developer does not handle this exception, it then passes to the operating system, which does whatever the OS wants to do, typically pop up a box or start a debugger or something. Every thread has a frame-based exception handler. It might not have anything in it, but it's there. So the thread environment block, right at the start, has the registration structure. And here's how it looks. It's just a series of pointers to next exception handlers. And the exception handlers are routines that will now look at the exception codes and decide to do something about it. And if it doesn't do something, it will return and try the next one and the next one. So this is just a series of sequential things it will do. And after they all fail, after they all just return without handling the exceptions, then it'll pass to the operating system. It will then pass on the block. So it's like tailor-made for us. You just get to run the code. So here's what this code looks like in C. I didn't even know C had try and except. I know Python does. You can have __ try, then cause an exception here. This will do an XOR of EAX with EAX and then call EAX. So it will try to call location 0, which is not legal. And then you have an exception here that will print something, oops. So instead of just dying with a Windows error message, it will just print oops on the screen because I handled the exception. This is how you write assembly code in C, which will then compile, and this would compile creating an exception handler. This is one way to do it. That's the sort of forward productive programming way to do it, as opposed to the way we're going to do it by just hacking in and overflowing and changing the numbers directly in the exception handler. You can see the structured exception handler in Immunity. Just view SEH chain, and it will show you the handler. There'll just be a series of pointers. And see, here they are, just counting up on this to these data structures on the stack, and each one of them points to a routine somewhere that will attempt to handle that exception. So you follow the address in the stack. You'll see up here pointer to next SEH record. And then there's the SE handler. And then there's other things here. And here's another, here it is. This is what it looks like if you just view it in the stack. So this is that pointer, SE handler, then some other control jump, then another pointer, then an SE handler, and on you go. That's just the raw binary structure of the structured exception handler. So, if you overflow the stack to overwrite the stored return address, you will find that you have done damage to other things, like you stored extended base pointer, you'll mess up the stack, you mess up other things, so you often do cause exceptions accidentally when you do buffer overflows. It's actually kind of tricky to make a buffer overflow that does not trash the calling program. All right, so if you want to gain control of this, EBX used to point to the exception registration structure. Now it's zeroed, like I said, in order to make exploitation a little more difficult. So in the old Windows process, you would just have EBX, and all you have to do is override it, go to the instruction handler and put jump EBX, and that will jump to the exception registration structure. I'm not sure I got that right. Anyway, here's a modern Windows process. When it crashes, you have nothing in the registers, but the third value in the stack points to the exception registration structure. You can see it up there, FFC4, and here's that FFC4 address, and this is the start of the exception handler. And in the buffer overflow we're going to do with vulnerable server, you overwrite this with text, 4D, 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 so you can contain that value. As you overflow the stack, you get a chance to change that process. Now there are protections. Each version of Windows adds more and more protections to stop every kind of exploit, and they've been putting in more protections to stop structured exception handler exploits. In Windows 2003 server, as discussed in your book, it checks to see if the handler is on the stack, then it's invalid. It won't let you do that. If it's in a loaded exe or DIL, maybe. It has some rules for that, otherwise valid. That's some attempt to detect if the structured exception handler is going somewhere inappropriate. If modules are marked not allowed, if it has no load configuration directory, these are attempts to detect forged, hacked, fake modules that you're jumping into. So there are ways to do this. You can abuse an existing handler, put code in an address outside of all modules so it will not fit any of those conditions, or find a module without a load configuration directory. These are different kinds of places you can hide code. And we'll be doing, if you did the projects for today, 8A and 8B, you're beginning to clue how to hide code inside an executable. There was going to be an HC, I didn't get around to writing it, where the original guy that wrote this wrote a program called Find Cave, I think, which will find code caves in your executable, which are just blocks that are not used. I didn't know this, but every executable has large blocks of bytes that are just not used, and you can just put extra code in there and jump to it. Anyway, so the defenses in Server 2008 get fancier. All right, now here's the normal SEH attack from Microsoft. You have, an exception will cause this value to be called as an exception handler, because here's the pop return, and I'm not sure I can make any more sense out of this diagram right now. Here's the exception handler going to various exception handlers, okay, and here's the end of it, telling us the end of the chain. So here, I change that value to point to this other value, which is a location in memory that happens to have a pop return. So when I trigger an exception, it will do pop return, and that will jump to an address, which was also on the stack. So that's how you can redirect code. Now, SafeSeh is a Visual Studio compiling switch, and this creates a white list of exception handler addresses, which is really quite clever. You remember we had something similar with DIL registration. There was registry keys that said certain DILs had to be loaded from certain locations on the disk, so you could not use companion Trojans anymore. This has a list that just says only these values are available for exception handlers, which makes a lot of sense. I mean, there's only maybe 50 exception handlers in your system, so those ought to be the only allowed addresses. You shouldn't be allowed to have any other exception handlers, and that's the plan. So modern code that was compiled with this switch will not let you change the exception handlers. It's built into the code from the start, what exception handler is allowed. SE hop verifies that the exception handler is intact before using it, which is another clever one. This is like Cisco's check heaps. They use to clean the heap on Cisco routers. They just walk every heap every structure to the next, to make sure that there's nothing broken. And as you can imagine, the buffer overflow technique where you overwrite these numbers tends to trash the integrity of the exception handler. In all of the exploits I've done, it creates an invalid exception handler. And this one will not let you use an invalid exception handler chain. So that's a good thing. Here's an exception registration record. This is what it looks like. You've got the pointer to the next, and then a handler, and then you have some registration records down here. It is very much like a heap. Each one has a link to the pointer to the next one. All right. So SE hop adds an extra registration record at the end of the list, and what it does is it walks the whole thing to make sure it hits the one it put at the end. And if you've been tampering with it, it will be broken, and the forward pointers will not link together, and it won't get there. So that's good. And there's SE hop. There's a valid SEH chain. You look at the first one. It has a next that points to this one. The next points to this one, and here's the final one that it put in there for this test. Here's what happens as a result of a buffer overflow. You've got a next pointer, and the next pointer points to some address here, which points to code I'm going to execute, which is shellcode, which is not really anything like an exception handler structure. And that will be detected by SE hop. SE hop is in our Windows Server 2008, and you will have to turn it off to do the SEH exploit. On servers, this stuff is typically turned on by default. Microsoft makes servers more secure, and they're talking about building Emmet. Emmet is the Enhanced Mitigation Experience Toolkit, which you can add to any version of Windows, and it turns on a lot of advanced security features, which are quite powerful, but they tend to break legacy code. So Microsoft is much pickier on servers than clients. On clients, they typically have these advanced security features turned off because many people want to use legacy code. On servers, they turn them on by default because they really don't want you using legacy code on the server. And it's the same as I think I mentioned before. If you have a client, it has a very large selection of device drivers and a very much smaller selection of device drivers on servers. So one thing I found that irritated me around the time of 2003 is I would have a machine running XP, then I would get 2003 and install it, and it stops working because there's no longer a driver for my NIC. So I have to go find the XP driver and import it because Microsoft is trying to discourage you from running servers on cheap, crappy hardware with cheap, crappy drivers. They want you to use drivers that are actually certified for use at Windows, which means that the developer had to pay a fee and submit it to Microsoft and go through Microsoft's testing. And then they would give you permission to stamp on the box, designed for Windows Vista, designed for Windows 10. And then that supposedly guarantees that it will not cause the blue screen of death when you run it on that operating system. And you are not required to do that. The cheapest NIC cards and everything don't do that. They just send you like a floppy disk with whatever driver, and typically the developers just took their driver from some really appalling old system like DOS or Windows 98 and just changed a few flags so it won't complain about the new OS, and it sort of works and it sort of doesn't work. And that's why your NIC is so cheap. You're going to the lowest quality of everything, including the driver. Anyway, so that's the game here. SE hop is enabled on server operating systems and disabled on client operating systems. And so you can control it with this registry key called Disable Exception Chain Validation. You can turn it on your Windows 7, you can turn it off on your Windows Server, and that's what I spent all day doing. I turned it off on Windows Server and rewriting the project to use Windows Server. Last time I taught this class, the exception handler project required Windows 7, and that's not necessary. I got pretty far down there, but I didn't quite get it all working before we came here. So what'll happen if you have SafeSeh on and you corrupt the SEH is it will not accept it. It will detect it and say debug program is unable to handle the exception. All right, so I got a few iClicker questions about that, and then I want to do some demonstrations. Somewhere is my iClicker app. There it is. All right. And someone else wanted to show us some things from the CTF, which I think is the most interesting thing to do today. I'm not going to, I think, go through the SEH exploit today. It's not due for a while. I'll do it next time after I get it perfected, because it's still got a few bugs that when I was working on. I'm making it much cleaner than the original one, but it's taking some time, and I'll have it by next week. So let me start this thing listening. All right. So, which defense is enabled in servers and disabled by default in clients? All right. So quit at 30. All right, and that is SE hop, that hops through the thing and makes sure the chain has not been messed with. SafeSeh is not an operating system component, it is a compiler switch. All right. So, which one cannot protect legacy code? I'll quit at 30. All right, and that, of course, is SafeSeh. That's the problem. See, if you change the operating system, then it protects legacy code or breaks legacy code, and that's, but if it's something in the compiling, then the only way to fix it is to recompile the code, and that will only happen with a later version. So that's the problem with a defense like that. All right. All right, which one can be enabled individually for each process? I'm going to stop at 30, and then I'm going to scroll back because I'm having second thoughts about this one.
I don't think you went over that.
Well, I think you can do it to both of these, for example. I know SLR can be turned on and off. It's on some processes and not others. Let's see if there's some statement back here that's clear about this. And I know you can turn SE hop off with a registry exploit, but I think it affects the entire machine. So where is it? There's a there. There, it's in here. Yeah, there's a registry. It affects the whole machine. I don't know. I can't find it now.
Are you looking for an X?
I'm looking for the registry thing. There's a registry. There, that's it. This affects the entire machine. It's local machine software, current version, image file execution options. Oh, vulnserver.exe.
No, that's so.
Oh, so it is turned on off for each executable separately. Then I don't understand why I had to restart the machine after I did this, but anyway.
We have to restart the process.
Maybe that's all I had to do. Anyway, this does seem like you can control it, you can turn on SE hop for each individual process. However, the reason why I'm worried about this question is I'm pretty sure the same thing is true of ASLR. Because, let me just skip to the project I was talking about, which I'm going to replace this one with a version designed for Windows Server 2008. But this one here will have the MOANA, which is going to show you when you run MOANA, which you'll do here, it tells you what defenses are turned on for different modules. So here are the modules, various parts of the program running like Bowne server and kernel-based.dil, and each one of them has these defenses turned on or off. This is whether it's rebased, which is, remember, whether it's loaded at a non-preferred location in memory. This is SafeSeh, which is turned on or off. Here's ASLR turned on or off. Here's NX enabled on or off. So that's why I say each one of these can be controlled. And the problem is there's usually some clown like this on your system, false, 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 where all this stuff is turned off, and therefore that's your doorway in. Anyway, all right. So I'm not going to grade that one because I think the answer is actually close to all of the above. Anyway, let's try another, see if the rest are any better. All right, which exploit method works only on Windows before XP SP1? Okay, that one I remember. All right, now I'll quit at 30. All right, and that was EBX, which I think at the time of an exception, EBX that had a pointer that was useful. This is an information disclosure vulnerability where then those are quite common. That's another way to overcome ASLR, by the way, is find something that leaks an address. And many code does have things like that leak addresses. But in this case, it's one of the registers that has something that leaks the address. All right. Which exploit method will defeat ASLR? Right, for simple stack overflows. By which, of course, I mean the targeting the EIP, the original kind. All right, I'm quitting at 30. And that's jump ESP, commonly used there. All right, which is not a popular answer. But see, a simple stack overflow, you do not target the exception handler. You just overflow the frame and get the stored EIP. And then, if you use jump ESP, you can jump to your injected code without knowing where it is. All right.
But you haven't been able to do that for a long time, right? I think that's been
You can still do
patched
that.
for a while.
No, it hasn't been patched at all. That's the simplest case of return-oriented programming. Oh, but you mean the stack is not executable? Well, no, that's correct. So what you have, since the stack is not executable, you have to overcome that with a ROP chain, which MOANA will get. MOANA will automatically find a series of instructions which you can run, which will turn off the NX on the stack. So then you can execute the code on the stack. That's the problem. I mean, there has to be some way to turn it off. So all you do is turn it off and then it's gone. Anyway. But that did slow people down by about a year in the exploits. All right, which one was used by the first stack overflows before ASLR? Quitting at 30, and we'll talk about these options. All right. Good, okay. So I mean, the point is, you can directly put an address here that goes to your code, and that's the original plan. But after they make the stack movable, so you can't find it, then you put an address here that points to a jump ESP. And now you can hit yourself on the stack. But now that they also turn NX on for the stack, so you can't execute code that you put there, you don't just do a jump ESP, you have a whole chain of jumps that chain together machine language instructions to turn off NX, and then a jump ESP. All right, which we'll do in the Defeating Dep with ROP project.
Can you do like arbitrary code with the ROPs?
You can, I think, in principle. In practice, you're of course restricted to whatever code it can find, but in fact, there's a lot of code, and you need a tool to help you find it. And what MOANA does is it has like 6 common things you want to do, and it finds candidates that can do that. And it will find like a dozen chains that do anything you want to do. And in fact, I've got it here. We'll go through it in more detail next time, but since you brought it up, let me show you, because I've got it right here in my, let's have a new window. Not that one. Oh, this is, okay, okay. CD documents is where I put it. Okay.
There's a ROP challenge on EasyCTF.
Is there? Yes, I saw that, yeah. So here's ROP chains, and here there's stack pivot chains. There's a few of these. So let me do a couple of these. You can do notepad, ROP chains. Okay, so here are the ROP chains it found on this Windows system, and here's the kind of thing it does. Here's how it turns it off. So for Virtual Protect, it found these instructions, chained together a bunch of them, and here's the ROP gadgets. So you define a ROP chain, and it goes to each of these addresses, and each of these addresses, it finds just a couple of instructions, like jump ESP, and it chains them together to do it. And so it gives you a list of ones you can use. These things here, there's 4, 5, 6, 7 of them you can use and more. Those are candidates that will do the same thing, and these are ones that will turn off DEP, I think. The other one, which I used in this first project, is a stack pivot, where you jump to the stack and then use it as an address to jump somewhere else. And I found a bunch of them you can use. And that's what we're going to use in the project.
So you don't directly execute something on the stack?
You what?
You don't directly execute from the stack?
Yeah.
Okay.
You get an address from the stack and you use it. So basically this is the one you do with pop-pop-ret. With pop-pop-ret, you use an address that's on the stack, but you don't actually, here's all the pop-pop-rets it was able to find, about 20 of them. So all I have to do is override an address anywhere, like the structure acceptance handle or anywhere, and if I put in this address, it will then execute pop-pop-ret and go to an address off the stack. So anyway, that's the kind of thing MOANA does for you, and it's really very nice. And it doesn't even take very long to do it anymore. Used to take a long time, because that's a huge search. This stuff would be pretty painful to do by hand. All right. So, which one is a register pointing to the TEB, the thread environment block? All right, I'm going to quit at 30. All right. And that is FS, which sounds great, but you can't do much with FS. There isn't a jump FS command or anything like that. But I think you can use it various ways. Anyway, let me see if I can determine any winners here. Let me turn off the recording. I'm going to make a separate recording of the stuff that has to be delayed for a while. This is 127, Chapter 8A.